Number 1. How does one find the domain of the quotient of two functions f divided by g? Basically, you just find the domain of f, find the domain of g, and then take their intersection, whatever their domains have in common. You don't want to take their unions, but their intersections. So, to be more specific, any numbers that make g equal to 0 cannot be in the domain. The g, remember, is in the denominator. So you can't have 0 denominator. So you'll also check for other domain restrictions on both f and g. If you have even roots, for example, all right, you can't have negative numbers in those even roots. You can't take the even root of a negative number, that is. All right, so watch out for those. By even root, I mean square root. The index of that root is 2. The fourth root, the sixth root, so on. So basically, you just take their intersections, the intersections of the domains of the numerator and the denominator, and that'll give you the domain of the quotient. Number 3. If the order is reversed when composing two functions, can the result ever be the same as the answer in the original order of the composition? If yes, give an example. If no, explain why not. So, the answer is yes, and here's an example. Let's let f of x equal x cubed. And let's see, g of x is the cube root, or x to the 1/3 of x. G of x is the cube root of x, or x to the 1/3. Okay, so what's f composed with g? F composed with g of x is equal to f evaluated at g of x, and that's equal to f of x to the 1/3, and that equals x to the 1/3 cubed. Now when you're raising a power to the power, and remember, if there's only one term here, if there was a binomial or a trinomial or something in here, you couldn't use this rule. But there's only one term in here, and it's raised to a power, and that's raised to a power. You multiply the powers. So that's equal to x to the 1/3 times 3, which is just plain x to the 1, or x. All right, and that also happens to equal g composed with f. And try it. Try g composed with f. G evaluated at f of x. So there's an example. Okay, number 5. Given f of x is x squared plus 2x, and g of x is 6 minus x squared, find f plus g, f minus g, f times g, and f divided by g. Determine the domain for each function in interval notation. Alright, so starting, well, let me write these functions. F of x equals x squared plus 2x, and g of x is 6 minus x squared. Okay, let's do f plus g. So that'll equal f of x plus g of x. What's f of x? X squared plus 2x. And then you're adding to that g of x, which is 6 minus x squared. Now since I'm adding, I don't have to worry about parentheses here. If I was subtracting, however, then I would have to put parentheses around g of x because I'm subtracting both terms, and that'll change the signs of both of these. However, adding won't change the signs, so it's not necessary to put parentheses here. Just remember that this part is f of x and that part is g of x. And there's f plus g. So this is equal to, just add the like terms, right? X squared minus x squared is 0. And that leaves you with just 2x plus 6. And that's all the simplifying you can do there. So there you go. The domain of this, well, this is a line written in slope-intercept form. The slope is 2 and the y-intercept is 6, a straight line. And of course the domain for that is infinity, negative infinity to infinity rather. Negative infinity to infinity, or all real numbers, is the domain. And now we have f minus g. So that here we go with the parentheses. X squared plus 2x minus parentheses 6 minus x squared. So here's f of x, these two terms, minus g of x. All right. So this is equal to x squared plus 2x minus 6 plus x squared. And so you add your like terms, you're getting x squared plus x squared is 2x squared. 2x, so you just have the 2x and the minus 6 left. They don't, they're not like terms, so you just leave them that way. 2x minus 6. So 2x squared plus 2x minus 6. This is a parabola, and since the leading coefficient is positive 2, it's positive, the leading coefficient. That's the point. The 2 is kind of immaterial there, but it opens upwards since the leading coefficient is positive. So there's a parabola. And the domain for that is all real numbers, or written as an interval, negative infinity to infinity. And then we have f times g. So that equals x squared plus 2x times 6 minus x squared. And you can use the FOIL method, or if you don't want to remember that little shortcut, just go this term times both of these and that term times both of these. In fact, that little rule will work on any kind of multinomial expressions like this where you're multiplying them. Okay, so you multiply each term of the first factor by each term of the second. So if there were 3 terms here, you would go the first term times each of those, second term times each of those, third term times each of those, and then you would simplify. Okay. So x squared times 6 is 6x squared. And then x squared times negative x squared is negative x to the 4th. Now you multiply this term times both of those, now you go to the next term. 2x times 6 is 12x, so that's positive 12x. And 2x times negative x squared is negative 2x cubed. Alright. Alright. So writing this in the usual order, in descending order of powers, that's the way we usually write this. It's negative x to the 4th minus 2x cubed plus 6x squared, and then plus 12x. It's not that written this way it's incorrect, but this way is the customary way to write those. Okay, so all the powers are nice and in order, descending, and it's better to look at, more organized. Okay, and this is a polynomial function, and all polynomial functions have all real numbers as domain. So the domain is negative infinity to infinity. And let's see if I can write this over here. Put a little dividing line here. F divided by g. So that's x squared plus 2x divided by g of x, which is 6 minus x squared. Now if you want to quickly figure out what the domain is for the denominator, 6 minus, let me see if I can go over here. 6 minus x squared. You can write that as a difference of squares, believe it or not, because this is square root of 6 squared minus x squared. So you have a difference of squares, okay? So that's a squared minus b squared is a plus b, a minus b. All right? So x squared plus 2x, and factor the denominator as a plus b, that would be square root of 6 plus x, and then a minus b is square root of 6 minus x. So even though 6 isn't a perfect square, you can still write that as a difference of squares. And that might help you sometimes. All right. Now, what can x not equal? Well, on top, this is just a polynomial. It's a parabola, and the domain of the numerator is all real numbers. Okay, so that's not a worry. It's the bottom that's a worry. All right. You can't have the denominator equal to 0. So x, as you can see, written this way, it's pretty easy to see what x cannot be. It can't be the square root of 6, because that would make this 0 here, or the negative square root of 6. That would be a problem there. All right, that would be 0 times something else would be still 0. All right, so x cannot be plus or minus the square root of 6. All right. So let's write that as an interval, like the book has instructed us. Let's see. So that would be negative infinity to negative square root of 6 union negative square root of 6 to square root of 6 union square root of 6 to infinity. All right. So there you go. Okay, number 7. Given f of x is 2x squared plus 4x and g of x is 1 over 2x, find f plus g, f minus g, fg, and f over g. Determine the domain for each function in interval notation. Alright, so let me write the functions. F of x is 2x squared plus 4x g of x is 1 over 2x. And 2x, all of that is in the denominator. All right. So what's f plus g? That's 2x squared plus 4x plus 1 over 2x. Pretty easy, huh? 2x squared plus 4x, there's f of x, plus g of x, that's 1 over 2x. Now, written like this, you might think, I can just leave it that way. It looks pretty easy, pretty simplified, but actually this is not a polynomial, all right, because of that last term there, 1 over 2x. If you wrote that as something without a quotient there, you would use 2x to the, actually you would use 1/2 x to the minus 1 power, 1/2 x to the minus 1 power, right? 1 over 2x is 1/2 x to the minus 1 power. Okay? Now in a polynomial, the powers on the x have to be 0 and up, positive integers, or let's say non-negative integers. So it can be 0, 1, 2, 3, 4, 5, 6, and so on. But in a polynomial, you can't have negative powers like here. Okay? So this isn't really a polynomial function, so you wouldn't consider this really simplified. Okay? So let's write it as a rational function. Since we do have a rational function at the end here, we can get a common denominator. That would have to be 2x, of course. So you've got 2x squared, multiply that by 1, but I'm going to choose 1 to be 2x over 2x. That'll give me a denominator of 2x on that first term. And then plus 4x, and then again multiply by 1, so you're not changing it, but you are changing its form. And I'm going to multiply by 2x over 2x again, because that'll give me the common denominator. And then 1 over 2x is already written the way we want it, so nothing to do there. Alright? So this is equal to, think of this as 2x squared over 1, and then just multiply numerators and denominators. Alright, so you get 2x squared times 2x is 4x cubed over 1 times 2x is 2x, plus 4x times 2x is 8x squared over 2x, and then plus 1 over 2x. Now they all have the same denominator, so now you can just add the numerators. So this equals 4x cubed, cubed, plus 8x squared, plus 1 over the common denominator of 2x. Alright, now it's a rational function, and that's considered simplified. Okay. The domain would be, well, what about the numerator? Well, that's just a plain old polynomial function on top. It's got an infinite domain, all real numbers. The bottom, the denominator, cannot equal 0, so x cannot equal 0. Alright? So anything works in this function except for x equals 0. So the domain then, written as an interval, is negative infinity to 0, not including 0, union 0 to infinity. Okay? So that takes care of f plus g. Do some quick erasing here so I can make room for the other ones.
A few moments later.
All right, next we have f minus g. So again, f of x is 2x squared plus 4x. And then g of x is 1 over 2x, so it's going to be minus 1 over 2x. This is almost like f plus g, all right? Again, we get common denominators. If you remember from the previous example we did, using common denominators, we get 4x cubed over 2x plus 8x squared over 2x minus 1 over 2x. Alright, so you do that just the same way as you did with f plus g. And so now that they have a common denominator, you can just work with the numerator. So you get 4x cubed plus 8x squared minus 1. And then all over the common denominator of 2x. All right. Same domain with this. The numerator here is a polynomial function. It's got all real numbers in its domain. So the denominator, however, cannot equal 0. So the domain is everything except 0. Negative infinity to 0, union 0 to infinity, not including 0. All right. Okay. I think I have room for f times g here without erasing. F times g. By the way, you could write f dot g dot representing multiplication. That would be okay if you wrote that. However, you don't use that little open circle. Make sure it's a solid dot, okay? Because that's not the same thing. That's f composed with g, which is totally different, all right? And that's what this section's all about anyway. So, to avoid confusion in this section especially, right, might be better just to write fg just next to each other like that without any symbols in between, all right? So, let's see, f is 2x squared plus 4x, so put that in parentheses, 2x squared plus 4x times g, which is 1 over 2x. There you go. All right. So think of all that as being over 1, right? You could write over 1 if you want. So you're multiplying two fractions. So 2x squared plus 4x times 1 is 2x squared plus 4x. And then 1 times 2x is 2x. All right. Now there's a little bit of simplifying here, which you could do. You could factor a 2x out of the numerator, right? So you got 2x, and that leaves you with an x plus a 2 in the numerator, and then 2x down below, and those will cancel. And so this is leaving you with just x plus 2. Now that's a straight line. Slope is 1, y-intercept is 2. The domain for that is all real numbers. However, be careful here. The original function was this, okay, before we did some canceling. All right. So you have to pay attention to the original function here. The original function had a 2x in the denominator. You can't neglect that, all right? So if you conclude that this function equals this, that's almost true in terms of, well, when you draw it too. When you draw this, you can't draw just a straight, solid, straight line, okay? You've got to, when x equals 0, you're going to have a little hole there in your graph, okay? So you can write this if when you're going down here, down the procedure, when you get to this point, you could say this function equals x plus 2 if x does not equal 0. All right? So in other words, these two functions, this one here, this rational function, and that one, look exactly alike as long as x does not equal 0. However, if x does equal 0, this function has a hole in the graph. All right? That's because of when x equals 0, the 2x down below here becomes 0. And you've got a 0 denominator. All right? So you're going to have a hole in the graph. Okay? Look out. Those holes in the graph can bite you. All right? Especially on a test situation. So this function, this product equals this as long as x does not equal 0. Okay. So what's the domain? The domain is everything except 0. So negative infinity to 0, union 0 to infinity. Yeah, yours truly got bitten by this once on a calculus test. Alright, so the functions were a little more complicated than this, but it's basically the same idea. Alright, so, you know, canceling has some risks. Okay, canceling does have some risks, especially when you're working with these rational functions. Alright, so you're tempted to think, oh yeah, this is equal to that. Well, yeah, almost equal. Okay, but the domains are different. The domains are different. This one has all real numbers as a domain, and this one has all real numbers except 0 as domain. So keep that in mind, okay? All right, let me do some quick erasing here.
1 minute, 37 seconds later.
Okay, let's do f divided by g. So we've got 2x squared plus 4x over 1 over 2x. Now, let me discuss a little bit about the domain before we get to that part, now that I'm thinking about it. Alright, this whole thing, the 1 over 2x, is the denominator of this function. Alright? However, you can't let that can't equal 0. Now, how is that going to equal 0? 1 over 2x. The numerator is 1. It's constant. Okay? No matter what x equals, this thing is never going to equal 0. It's going to be 1 over some positive or negative number. Alright? What if x is 0? Well, then it's undefined. It's not going to equal 0. This 1 over 2x won't equal 0 if x equals 0. It's going to be 1 over 0, which is undefined. Okay? So you don't have to worry about 1 over 2x equaling 0, but you do have to worry about the 2x equaling 0. Okay? So when we simplify this, the denominator here might go away like it did in the previous example, but we have to keep in mind that in the original function x cannot equal 0. Okay? So keep that in mind. Alright, well, you just, when you're dealing with these complex fractions, you invert the bottom fraction and multiply by the top. So this is 2x squared in parentheses 2x squared plus 4x, and then invert, make that a 2x over 1 times that. Alright, so it's just 2x. 2x over 1 is just 2x. Okay, so you multiply that, you just distribute the 2x through, you get 4x cubed plus 8x squared. Now, that's a nice polynomial function with an infinite domain. All real numbers, that is the domain. However, remember, x cannot equal 0, all right, from the original function before we did all this simplifying. Okay, so I'll say this f over g equals this polynomial function if x does not equal 0. So there you go, okay? So the domain, and again, if you graph this polynomial, and then you graph this, they're going to look exactly alike except at one point when x equals 0. There's going to be a hole in this graph here which won't appear in this graph, okay? So this graph is continuous. Polynomial functions are continuous. There's no breaks in them, okay, no holes. But this function here does have a hole in the graph, a discontinuity, when x equals 0. Okay, so the domain is negative infinity to 0, union 0 to infinity. And there you go.